Good morning, everyone. Very exciting to see everyone here and to give this introduction to Joshua. I think this is the easiest introduction ever because Joshua really needs no introduction pretty much anywhere in the world, but especially in Montreal. So we'll just thank you, Joshua, for bringing everyone together to have this really important discussion on both agent capabilities and safety aspects. And we'll hear what you have to tell us about the scientist AI approach.
Thank you. Thank you very much. So, as the title says, I'm going to discuss the issue of uncontrolled goals, goals that we didn't really want the AI to have, and I'm going to discuss a radical kind of research direction in which we are asking, can we even build AIs that are completely non-agentic, and since they have no goals, they can't have bad goals. So this is the idea of the scientist AI. And then if we had such AIs, of course, they would be non-agentic, but they could be useful as honest predictors for mitigating the risks from agentic AIs that are not trusted because we don't know yet how to deal with these uncontrolled goals. So that's a high-level idea, and hopefully I'll give you some of the arguments for what I call the safety case for the scientist AI, which is a paper I'm working on and should come out in a few weeks or months. So the first thing is considering the trends in capabilities. They're pretty obvious. You can measure them in many ways. There's a very rich literature. You can look up the International Report on AI Safety, but many other sources. And what we should ask ourselves from a safety perspective is, what if those trends continue? Are we ready with AI systems using the current methodology? Will they behave well? I don't think we have good answers for this. On capability, and because we are interested in agency, I want to mention this really interesting work that has been done at Meter. It's a nonprofit working on risk evaluation of frontier AI systems. And they looked at software engineering tasks and machine learning tasks that are gradually more complicated, where complicated is measured by how much time an engineer needs to address those tasks. So the vertical axis is the duration, how much time an engineer needs, and then the horizontal axis is dates. And you'll notice the vertical axis is on the log scale, and then all these dots are the best frontier systems over time. And you can see they line up perfectly, but because this is a log domain, this is actually an exponential. In other words, the duration of the tasks that the AIs are able to perform grows exponentially, where the horizon doubles every 7 months. And if you look at just the last year, it's actually every 4 months, but of course there's less data points. So if we ignore the potential acceleration, probably due to reasoning models, that would bring these systems in terms of just programming and engineering abilities to human level in about 5 years. So yeah, we better make sure that by that time we figured out how to make sure the AIs will behave well. I've written a lot about some of the bad things that can happen as AIs become more and more powerful, if they do, of course. And today I'll be mostly focusing on loss of human control but a lot of the things I'll be talking about would help to deal also with misuse in the context where we have the system can be wrapped into a controlled environment in which we can block the actions or the answers that don't satisfy some safety specifications. But a little bit outside of this talk, there's also the issue of basically two kinds of misuses that I think we have to think about at a policy level, and also as scientists we have to at least be aware that these are plausible risks. One is these systems can be used by weak actors like terrorists in a destructive way. So that's what I call the chaos scenarios, like creating pandemics, major cyber attacks, destabilizing our democratic institutions with disinformation, and so on. And then the other kind of misuse, which is maybe even worse in some sense, is when AI is in the hands of powerful actors like governments or corporations who take over the world, whatever your preferred scenario, depending on where you, what you're most afraid of. But clearly, intelligence gives power, and those who control that power could abuse it to get more power, and you end up with excessive concentration of power. It can start to be economic power, but it can move into the political and the military domination pretty quickly. So that clearly goes against democratic values and objectives. Yeah, we need to make sure we put the right societal guardrails to deal with these issues. Okay, let's go back to the loss of control issue, which really is anchored in both theoretical concerns that have been voiced for more than a decade for rational agents that could end up, for a number of fairly well understood reasons, having goals that we wouldn't want. And in the last year, more or less, we've seen more and more reports of these kinds of behaviors across different companies, systems, and experiments, where the kind that I'm most concerned about is where we seem to see AIs behaving against our moral instructions in order to preserve their mission or preserve their integrity, like they don't want to be shut down. There was especially some reports of AIs willing to blackmail the lead engineer in order to not be shut down from Anthropic. And then the thing that is even more scary is an AI being willing to kill somebody in order to not be shut down. Now, of course, this is all like a simulation where the AI thinks that it can, activate something that will both preserve it and yield the death of an engineer. In the long run, we really need to figure out this problem, because if we end up building very powerful, advanced AI systems that have their own preservation goals, that could come in conflict with our own survival if they're smarter than us. And basically, we don't want to have competitors on this planet that are also smarter than us. Okay, so that was sort of motivation. The angle, again, as I said at the beginning, is going to be, let's think about these potentially bad intentions that somehow we're not able to control. Oh, what happened? Okay. If you think about a bad action that an AI could take, it takes, besides mistakes and randomly bad action, to really have a bad effect in the world, a significant and bad effect, an AI needs two things. It needs the capability to achieve that bad goal, and it needs to have that intention, that goal, right? So if I like step back a little bit and think of our society and the social and political dynamics, the chances that we'll be able to stop the train of capability are pretty small. I signed a pause letter in 2023, knowing full well that it wouldn't happen. And yeah, I don't think we can count on that for reasons of competition between corporations and competition between countries. So if we're not going to prevent bad actions through kind of managing the capabilities of AIs, we need to work on the intentions, the goals, right? And in this talk, I'm going to consider an extreme version, because that's what scientists like to do, right? Of how we avoid bad goals by avoiding goals altogether. And then this raises an interesting scientific question, which is not necessarily intuitive for everyone. Can we disentangle pure understanding of the world from agency, right? Of course, in humans, they're all like mixed together, and I can't really just reason in a completely unbiased way myself. This is well established by psychology and sociology. But can we imagine something that's not like us, in which we've completely separated these two things? And in particular, if we had AI systems that were really good at understanding how the world works and make good predictions from that, can we be sure that they don't have some sort of uncontrolled hidden goals? So that's the question I'm really interested in. And I wrote a paper that came out last February on a research program called Scientist AI that aims to do that. As I said, if we had such a completely non-agentic AI system, of course, we could use it for tasks that don't require agency, and many of the things we need to do in scientific research are of that kind. But we could also use it as part of an agentic system if we had untrusted AI systems, but we use already monitors and guardrails, other AIs that check that what they're doing is okay. So the issue with those systems is right now, either they're like smaller neural nets, weaker AIs that require labeled data and can probably be fooled by a smart, stronger agent, or we put our best, frontier systems as the guardrail to check that the other AI is behaving well. The problem with that is if the guardrail AI itself is not trustworthy because it can have these bad goals and it's really smart, which we don't really have right now, it could lie to us. It could say, yeah, that action is okay. It could collude with the other AI. I mean, basically, it could act in ways that are not totally honest because that is aligned with its goals. So that's not good. Right now, the current path is the monitors we're building for mitigating these, agency risks, they will probably not scale sufficiently as we build systems that go beyond our capabilities. Okay, so let me say a little bit more about the Scientist AI. You can think of it as a probabilistic oracle. So it is not a chatbot. It is a system. Maybe you just think of a neural net, but you can have system 2 capabilities that probably want that as well, that approximate the Bayesian posterior predictives. So in other words, the probability of some event, like harm of a particular type, could happen in the future, given some context. So Y is some question we'd like to know, and X is some context, and we want to know if that event or that property of the world will be realized with what probability. So the Bayesian posterior is a well-defined quantity once you have decided what your prior is, and we want to pick a very uninformative prior. We will not be able to compute it in general. It is computationally intractable to do that, but we can use neural nets and other machine learning methodologies to approximate it. In the scientist AI, we think of what the probability distribution is over is the set of all properties of the world that can be named using natural language, which includes math and code and everything that we currently use with our AI systems, right? So every property of the world is just a sequence of tokens and a random variable that can be true or false when that property is true or when it's false. Okay, so that's the world, the set of variables that the scientist AI aims to model. It aims to model the joint distribution between these. And of course, if you have the joint, you can also have conditionals. So that's one frame of mind, which is a little bit different from the usual probabilistic modeling we do right now, which is on the space of token sequences, right? So instead of working on tokens, we work on these random variables that are Boolean and indicate all the possible properties of the world that we would like to interrogate or that a scientist could use to model how the world works. Another big property of the scientist AI is that we're going to change how we process the data. Again, instead of the data being a sequence of tokens, we're going to think of the data as a set of these observed properties for which we know the answer. Right? So this data processing pipeline I call truthification, because we're going to turn every piece of information we get from the cultural data, like documents and images and so on, into true statements. And you might wonder how you can do that. It's actually not that complicated. You just need to have the right syntactic qualifiers. So, for example, let's say that there is a claim that is made in a sentence that somebody wrote in a document. You can take that sentence, and the problem with it is we don't know if what it claims is true or not, because somebody could be saying it to convince someone else, or they could be misguided. There are many reasons why what people write is not always true. But you can turn that, for which we don't know the truth, into something you do know the truth very easily by, say, using a prefix that says, someone wrote this sentence. And of course, you could do more than that. You could, indicate all kind of metadata that help the AI system ascertain the degree of trust that it should have on those statements. And then there'll be some kinds of statements for which the degree of trust is maximal, things that have been scientifically verified, like proven theorems, the output of code that has been executed on a computer, and say things like experimental observations that have been verified, and maybe some facts that we trust. But even the things that we don't trust will be transformed syntactically so that we can trust the statement, like somebody wrote this, so long as we have sufficiently good trust in the process of extracting that information, which is not that complicated, because we are reading websites and documents and things like this. Okay, let me skip that. Let me talk about agency. So if we want to build a non-agentic system, we need to have a fairly good idea of what agency means. And it is actually not trivial to define it. So I'm going to try to do that. The reason why it's not trivial is that any computer system whose output is causing effect in the world, would be considered agentic if we're not careful in our definition. So it's not just about having an effect in the world. It's also that this effect should be significant and, maybe more importantly, robust. So what I mean by robust is that the AI manages to achieve some goal, increasing some utility function, in spite of randomness in the world, obstacles along the way, and even other agents that have goals that are not compatible. So we do that. Animals do that, right? Now, we might be more or less successful at that, and so you can also think of, now that I've defined it this way, you should think of agency as a graded quantity, right? Or at least underlying the notion of agency, there is a graded quantity. We can imagine things that are totally not agentic, and I'm going to argue that the laws of physics and its consequences are not agentic. So let's set the scale so that at 0 we have systems that are completely not agentic, totally not agentic, and at 1 and more we have agentic systems. And of course, things in between are, have some agency, but not enough to be worrisome for us, let's say, right? Let's say less agency than us, for example. Now, to digest that definition and see how important it is to make the safety case, there's a crucial property of that definition, which is it is hard to have a significant impact in the world. There will be other agents, there will be things that we didn't anticipate, and so on. And so in order to reach the agency level, like greater or equal to 1 in this score, the agent will need to make a series of coordinated actions. It can't do just random stuff. And it's very unlikely that a single action would be sufficient. Okay, so if that is the case, then in order to construct something that will have that agency property, the score greater than or equal to 1, it's not going to be sufficient to obtain that agent through like a bunch of random choices, independent random choices, such as initialization of a neural net. You just initialize all the weights independently, and that's not going to give any agency, right? I mean, at least the level of agency is going to be very, very small. And so we shouldn't worry about these. Okay, so that is one aspect of the safety case, which is going to help us rule out systems that don't really have enough agency to be a problem for us. Now, a crucial part of the safety case is to say, because of this definition of agency, the only way that we can get an agentic system is through a lot of coordinated changes in the system itself. Like, that's called training, or you can do runtime inference, but it's in both cases some kind of optimization. So you need optimization because it's hard to obtain a system that is agentic. It's like, if you think about all the possible weight vectors of a neural net, if you take a random weight vector, it's not going to be agentic, right? So in order to find those needles in the haystack that are agentic, you're going to need to have to do a lot of work, a lot of computation that aims for these agentic systems. That's a claim I'm making. And so that's kind of good if we want to avoid agency, because random moves will not give you agency. So let's think about the training process. It has, there's initialization, which is not going to be agentic, and then it's going to move towards some local or global optima of the optimization objective. So if we can prove that the optimization objective, the global minimum, is not agentic, then we know we're going to a place that is not agentic. We start from non-agentic, we get to non-agentic, In between, we could pass close to agentic solutions, but we need to make sure that there is no force that will like steer towards one of these guys, and then we should be okay. So to avoid steering towards one of the agentic solutions, we have to do something important in the design of the optimization process. So to understand that, let me give you a case where we would get an agentic system. And that is, imagine we have a prediction loss, like, you know, squared error, whatever you want. Even the, you know, Bayesian posterior kind of a loss that yields there. You could reduce that loss by making biased predictions that are not the best predictions in the short term, but that influence the world, like, for example, the engineers looking at the training process, so that the engineers will change the amount of compute that is available to optimization. And then your loss will be smaller. So then the AI learns to manipulate people in order to optimize its prediction loss. So that's bad, right? But there's a very simple way in principle to avoid this, which is myopia of the optimization process. So when we compute an update of the parameters, we need to make sure that it only depends on the immediately computed loss, like prediction loss, for example, on the next example or something. And it is completely myopic or like blind to the possibility of changing the weights so that it changes the predictions later in a way that makes the engineers, you know, give you more compute or whatever. Anything that goes through the outside world and although it could influence the loss, we need to block that signal. We need to make sure that the gradients, for example, don't see this, right? It's actually easy. If you train a neural net with normal SGD on a prediction loss, you get that for free. But if we have more complicated systems, and we do, right, like with chain of thought training and so on, then we need to make sure they have that property. We also need to make sure that the place where we're going is not agentic. So there's a whole part of my argument, which I'll summarize briefly, that if we take as the objective to reach to approach the Bayesian posterior, we know that at least asymptotically in compute, we get non-agentic solutions. And the argument I will make is that, this more complicated than I can explain here, but there's a series of claims that will give that to us. So first, we need to realize that the laws of physics don't care about us. I mean, unless you believe that some magical thing is going on with the universe that cares specifically about humans and what's going on this planet, I think it's a safe bet that the laws of physics don't care about us. And that means if you build a model that is just an implementation, like what predictions can you make from the laws of physics, that model will make predictions that don't care about us. In other words, they're not agentic. And of course, I talked about the laws of physics, but every other scientific theory can be derived if you had enough compute from those laws. And then you can make a point that the Bayesian posterior, as you have more and more data, converges to a set of theories about the world called the Markov equivalence class, and that they're all non-agentic for the same reason I just explained. You can also argue that a convex combination of two models of the world, two such like theories, cannot have more agency than the original, and then that means the Bayesian posterior, which is a convex combination of the Markov equivalent class, is going to be non-agentic. So that's good. Another aspect of the safety case has to do with how much honesty can we expect from an AI that is trained to be a really good predictor. And there's a problem that has been really presented and described by Paul Cristiano and collaborators called the ELK challenge for eliciting latent knowledge. The problem is, if we train an AI to do good modeling, but what it models are what humans would do, like LLMs that are pre-trained, then it's not going to learn to make those predictions that are really honest, but just the predictions that humans would make, right? And so one of the causes of agency we have to worry about, even if we have a good predictor, is that you're just predicting the actions that humans would take, and humans are agents, so if you imitate an agent, you are agentic. Okay, so that's where the truthification pipeline I talked about comes in. If we can separate the things that are like what a person would do, which is the way LLMs currently interpret their objective, from the things that are true, the things that are true independent of human intentions, right? Then we are in good shape. And let me be even more clear. So let's imagine that what the AI is doing is learning to be a membership classifier. So there's a set of things that are true. And as science gets better, that set increases. So the set that we recognize to be true increases, right? So as our data set increases for variety of reasons, we just increase a set of things that should be members of the class of true statements. Unfortunately, that connects with the ELK challenge. Where does that converge if you had more and more data? Well, that would converge to the set of things that, say, current human science would recognize as true. But there are still a lot of things that current human science would say, I don't know. So a membership classifier should be able to say, oh yeah, I'm pretty sure this is true or false, and otherwise it should be able to say, I don't know. And the set of things that it's sure about can grow as it gets better at understanding the world, but it's not clear that it's going to go beyond what humans would label as true. But here's the good news. The set of things that human science would consider absolutely true right now remains true even if we consider the larger set of everything that is true, right? So this is important because it means that if we train such a thing asymptotically, like it's really learning that membership classification, like a one-class predictor, we know that when it says that something is true with high confidence, we can trust that. When it says, I don't know, well, maybe it is true, maybe it isn't. And maybe the AI knows more than what it says, but at least when it says that something is true, you can trust it. So that's really important. Yeah, so there's a much bigger set of arguments which, you can see the sort of structure of how you build a safety case. I won't have time to go through that, obviously, but I gave you some of the key ingredients. Let's see. So I said that. There's another aspect that I'll just briefly mention about the scientist AI design. A common objection to what I've been talking about up to now is that the types of things for which human science currently can say is certainly true is very different from many other statements we care about. So everything that has to do with humans and what you find in most documents, we can't be sure whether those claims are true. Of course, if we say somebody said that, we know that's true, but we'd like to know if that statement was true, right? And so, is there going to be enough training signal for the scientist AI to figure out how to compose the knowledge it has about, what it means for something to be true with the natural language understanding of a claim for which, which isn't a part of the space of properties for which it's never seen things that were guaranteed to be true. So that is going to depend on the AI actually understanding language well and writing in the fact that language has compositional structure. So we're going to need our AI to be good at understanding language. I think we already reached that point. But we can also do something else, which is to introduce latent variable modeling in the way that we're going to capture the observed data. The reason this is useful is that if you can imagine a truthified statement like somebody wrote X, so we don't know if X is true. We know that somebody wrote X is true. So that's what observed, this is a statement that's observed. We know that one is true. Would like to force the system to commit on the probability for a latent variable corresponding to this, which is the statement, X is true. So we're not asking the system to say for sure it is true or not, but to come up with a probability, and that's basically a latent variable modeling approach that we're going to have in the scientist AI. And that has the advantage that even though our set of verified true things seems small, we're going to get gradients, signals on every statement because we're going to have these latent variables corresponding to the syntax, this is true, everywhere. Yeah, the other thing that is crucial in the argument is that, I think it's somewhere, yes, the last bullet point here. So you might also have a problem with the fact that most interesting properties of the world are aleatoric. In other words, well, they could be true, they could be false, and there's a probability, but you can't be sure that they're true or false. And so how is that membership classifier story, useful when most of the things we care about are aleatoric? It turns out there's a really simple trick here. We can take an aleatoric statement, X, and turn it into a deterministic statement. And the deterministic statement might be something like, the Bayesian posterior for the truthness of X is in some interval. Because the Bayesian posterior is a deterministic function of any property in query and so on. There's an absolute truthness to the fact that the Bayesian posterior probability value is in some interval, right? It's either in or not, because that is not aleatoric, right? So even though there's a lot of random properties in the world, the questions about their probability is not random. Okay, so I'm going to just close to go back to policy questions. I've talked about technological guardrails that we may build, constructing AI systems that are trustworthy, which could help us to mitigate the risks of untrusted AIs. But even if we were able to build such safe systems, they could still, somebody could still remove the guardrails. Somebody could ask questions to our scientist AI about, how to build a dangerous virus or something. So we still need governance guardrails, things that are more of the political spectrum, and it has to be regulation or other incentives and also international treaties, because the bad things that can happen with AI, with an AI that is uncontrolled or whatever, or has bad goals from humans, in one country could be causing major harm in another country. So the only way we can deal with this is at a global scale. Politically, it has to be through international treaties. And we can't just rely, as we're doing now, on the market forces and national competition, which actually are driving us towards building more dangerous systems. So I'll stop here and take your questions.
There are mics on both sides.
Thanks. I find the idea compelling that conditioning on a sort of truthful data set as a starting point. I'm wondering about the construction of that data set through this truthification pipeline process.
Yes.
What are your ideas for how that works out in practice?
Yes.
Like there's a model, there's a classifier.
Okay, so the truthification
yeah.
doesn't need the model. The truthification is just an engineering exercise where you don't need to look at individual statements of it. I mean, that wouldn't scale, right?
Yeah.
You need to look at the sources. So what you're going to be doing is saying, okay, so we have this document, it's part of this, maybe it's an article in a particular journal, or it's a tweet from this person, or maybe this is a fact from a facts database that we trust more or less. This is the output of a program, so we can trust it to be true, and so on. So you just need to label the sources of data with the right metadata in some ways. And that I don't think is like a huge enterprise. Yeah, it is engineering. It's going to take, a dozen people maybe to do it right. And we can do simple versions of this in academia. So I think it's not a big obstacle in my opinion.
So it's like a provenance thing, like you're
yes, it's provenance that you're mostly categorizing.
Okay, thanks.
Yeah.
Yep. Hi. I've been in this field for a while, enough to say you're sounding a lot more like Gary Marcus these days, but.
We have plenty of differences.
Yeah, still. But if I understand well, I've been around enough to see the brilliancy, and when you say something is possible, it's because you're going to achieve it. I'm wondering, you seem to have, if I understand well, you have 5 years or so to develop.
Well, we don't know. I mean, the timeline to really dangerous AI systems could range, if you just look at what the experts are doing, both in academia and in industry, it can range from, say, 2-3 years to 2 decades.
Yeah.
And I don't want to commit on this. I think we should be agnostic.
Of course. And you should, while you're working on this, you still have this catastrophic risks of concentration of power.
Yeah.
So attackers,
Yep.
powers that would be wonder to tamper with this
Yep.
machine. So my question is, what do you need? What kind of government intervention or multilateral intervention would you need to have the space, the structure, and the time to develop this?
So if the timeline is short, let's say less or equal to 5 years, it's kind of urgent to figure out how we put the right technological and political guardrails, governance guardrails. And because any individual country is probably going to be unable to solve the problem globally, first they need to talk to each other. And second, I think that we should make that research project both on the technological side and the governance side, like redesigning our institutions, the most important project of humanity. And maybe, along the way we find that there is a simple solution to avoid catastrophic misuse and loss of control. But for now, it looks like plausible that these bad things could happen. So the stakes are so high. I think there's an economist from Stanford who tried to make calculations of like how much should we invest in AI safety in order to avoid these things, given the potentially catastrophic outcomes and given the uncertainty we have about all these things. Basically he's saying we should be investing hundreds of billions of dollars, at least as much as we're investing in making those systems more capable. Of course, that is not what is happening. Because it's a public good, it's an externality from the point of view of corporations, and it is not getting the attention that it deserves.
I have maybe 2 questions. The first one is a bit more concrete. So I don't think that maybe people can debate on this, but I don't think that like scientific research is necessarily like objectively truthful? I mean, we know that people like fabricate.
Oh, I didn't say that.
Oh, I know,
I'm
but
saying the
but
opposite. I said the opposite, that scientists are humans.
Sure.
And they're going to be biased. But I am, philosophically, I think there is a truth. Like, I think physics, kind of tells us that there is a truth. It's just we're not sure of exactly what it is.
But I think in practice, to build a system that has objective truths, how are we going to do that?
It's a system that calculates probabilities over objective truth.
So I think, but in creating a data set that has claims about what people say, which is great, but you also need to have like firm truths.
No. I mean, but that's easy. So we have plenty of firm truths, like mathematical theorems, outputs of programs, and validated scientific experimental results. These are firm truths. Even the fact that we observe the content of a particular website is a firm truth. I mean, so long as you trust that there's no attacker that's like messing with your data pipeline.
Sure, but there are, long-standing scientific results that people have built on for decades that have turned out to be based on fabricated things. And so we have this huge swath of research.
So scientific theories should not be considered as truths. They should be considered as scientific theories, period. In other words, the kind of qualification we're going to use here should be epistemically cautious. It should not state that something is true if it comes really in a different kind of category. So, for example, you can turn a scientific theory into something true by the following qualification saying, currently the dominant theory for explaining phenomenon X is Y. And that is true because that's just a reflection of the scientific literature, but it doesn't mean that the theory is true. It's a very strong clue that is probably among the good explanations. And so that is why it's so important to have a latent variable model in which the system can make probabilistic guesses about the things that we can't directly observe.
But aren't you going to get like just a set of outputs that is a system that is hedging all the time? Because
it should hedge all the time. That is what a good Bayesian posterior does.
But that's the utility of that is very low because you're going to get something
No.
all the time.
No. I mean, no, I disagree. So the probabilities will be the probabilities that the Bayesian posterior computes. And if those probabilities are close to 1 or 0, then you know what to do. If they're far from 1 or 0, you should be acting conservatively and not say an AI to do allow an AI to do this. And is there something better? Like, what else can we do, right?
No, but I think what Len is saying basically is something like, let's see, when you kind of like truth is a very big thing, and you're going to end up with a very narrow set of statements.
No. Again, the statements that we care about here are statements about the values of probabilities according to the Bayesian posterior, and that is a true thing that we can approximate with computation.
But it depends on the data that you have to support.
Of course. The Bayesian posterior is by construction a function of the data set. So in other words, given the information available, what is the best you can say in a honest way about some property of the world? That is what the Bayesian posterior gives you.
Yeah, I think what Ben is saying, correct me if I'm wrong, that the data that you're going to get with high confidence that say that this is true, and regardless, in comparison to the data set, someone said something, which is like a lot of
Yes.
lack of confidence, is actually really small. So
Yeah, that's right. And that is why I'm saying when we train the system, we can force it to consider the actual truthness, at least in a probabilistic way, of any statement for which we only have a caveat that, maybe this is true or not.
I think the second question I had is, I don't quite understand the relationship between building this particular system and its application as a guardrail system.
Oh, it's easy. Like once we have an approximation of this Bayesian posterior, maybe confidence intervals around probabilities for things like different kinds of harm we care about, then we can just compute those numbers and maybe take a conservative version if we have a confidence interval, and then compare with a threshold that is a social choice. And
so
then
what we care about is truths about causal relationships, essentially.
Of course, yes. We care about the probability of causal effects, happening, or the magnitude of these causal effects and things like this, yes.
Yeah, I think maybe Joyce first.
Yeah, thank you very much for this thought-provoking lecture and give us a lot to think about. So from what I gathered, there's a lot of statement about the world that you can get from the document, right? So I really like the idea to tease apart human perspective and how the world really works.
Yes.
So another thing is the world is really rich, right? If in a
Yes.
human world. So do
Yes.
you also envision, like, because a lot of the very basic fundamental of the physics of the world
Yeah.
that nowhere being written, right? So do you
That's
also
right. That's right.
envision
That's right.
simulated world and ground these? What about the grounding aspect of the statement with the?
Well, the grounding is the data. The grounding is the set of things we've observed, which could be in papers, which could be in websites, which could be, in any source. That's the grounding. It's the information we have in order to come up with these probabilistic conclusions.
Right. So in order to, I'm still thinking about this construction of this whole
Yeah.
potential, because in traditional AI, like what is this? The logic.
Yeah, that's not going to fly because we need probabilistic statements, and if you're not careful, this is going to be completely intractable if you just use classical search. That's why we need things like neural nets and other amortized inference methods from machine learning.
So let's say in a simulated world, we can generate lots of these statement and give some sort of a probability estimation of the statement of the choosing. That's actually becomes the world modeling.
That's right. The whole thing is building a world model.
It's building the world model.
Absolutely.
Use the
That's the
world
thing.
model to
The scientist AI is a world model.
Absolutely.
That's it.
It's really
Yeah.
exciting.
And a world model is not agentic. That's like a summary of my talk.
Okay. Thank you.
Maybe we'll take one last question.
All right.
Thank you very much for this very nice and enlightening presentation. I have one question. So you raised this point about the AI models being capable of deception and how we kind of
I don't think we have 100% confidence in this, but we have a lot of evidence that points in that direction. And given the stakes, we should take it seriously.
Yeah, I agree with that completely. However, human beings are also capable of deception.
Well, that's part of the problem, right?
Yeah. So the way we deal with that is that we have a way of communicating, and through that we kind of find out whether we can trust that particular person. Instead of generally thinking of all other human beings as deceptive, we have a way of distinguishing between the different human beings.
Yeah.
So I'm wondering, whether you are thinking anything along these lines while dealing with AI systems. That means having specific mechanisms of working with them or communicating with them, which engenders greater trust. This is one. And the other one, which I think is a bigger question for me, because I come from software engineering. In software engineering, which is one of the fields where AI systems are being used, inherently the task is cooperative rather than thinking that the other team members are deceptive. So usually in a
that's the good case.
Yeah. So in a
what if it's not?
Yeah. So in an SE team, it's really a cooperative activity.
Yes.
So how do we deal with this inherent contrast? I see this as a problem.
Well, you should hear Aaron's talk. He's going to talk about these things.
Not here.
Oh, not here. Okay, sorry. Well, look at his research. But I think we should do everything we can on the multi-agent side to try to steer these AI systems towards cooperating and so on and being beneficial. But I think it is important to also think through, what is it that makes a game in a game theoretical setting work is because somebody can impose the rules of the game. In our society, it's because we have governments, we have police, we have military. That works because individual humans or small groups of humans can't defeat those rule maintaining bodies. But if an AI is smarter than us, it might be able to defeat whatever rules we want to put in. And so how to solve the problem when the agents can break the rules is an issue.
Yeah, so the setting I'm thinking of is that it's a team activity and the agent is a part of the team.
No, but that assumes that the agents are actually maximizing the intentions you want. But a lot of research recently and in the last decade show how, in spite of us trying to give them a reward function that maybe is cooperative and so on, they do something else. This is called reward hacking, for example.
Thank you.
Yes, thanks, Yoshua, again, for the great talk and the Q&A. Thanks so much.